The element hydrogen has always been an interesting element due to its unique structure, the fact that it only has one electron, and this structure, when it comes to bonding to other atoms, imparts some unique characteristics as well. If we take a look at a common molecule containing hydrogen, methane, four hydrogens bonded to one carbon, we see that the electronegativity differences are fairly small, 2.4, and we would consider this a covalent bond. Not only that, we would probably phrase it or term it as a nonpolar covalent bond. Um, if we take a look at if we turn this scale on here, electrostatic potential, just a fancy name for the partial charges that you might expect to see, we see that overall the electron cloud tends to have more of a mid-range kind of grayish color, which would be about in the middle. You see a little bit of blue for the more electropositive hydrogens and a little bit of red towards the center of the molecule here for the more electronegative carbon. As we look at molecules that demonstrate more polarity in the sharing of those electrons, take ammonia for instance. Okay, nitrogen has an electronegativity of 3.0 compared to hydrogen's 2.1. So at a difference of 0.9, we would probably most likely classify this as a polar covalent bond. It's still a sharing of electrons, but it's a very unequal sharing of electrons, and you can see that the nitrogen end of this molecule has more of a negative charge to it, and the hydrogen end tends to have more of a positive charge. If we go to water, hydrogen, and oxygen, oxygen has an even higher electronegativity. We see the same behavior. The blue gets even a little deeper, the red gets a little redder, indicating that there's an even greater partial negative charge on the oxygen end, an even greater partial positive charge on the hydrogen end, thus creating even more polarity. And so these would be ammonia, water would definitely be considered what we call permanent dipoles. If we go to the most electronegative element that we have, fluorine, attached to the hydrogen, we've got the largest electronegativity difference here, and you can clearly see that that fluorine atom being so electronegative is pulling very, very hard on hydrogen's electron. Now, it has only one electron, which means that if it's being pulled away, it's exposing completely the nucleus of hydrogen, which contains only one proton. So essentially, when we say, we've judged these as being partial positive and partial negative charges, in effect, this is almost a full-blown positive charge. And so what this means is that when we have compounds of hydrogen that are bonded to very electronegative elements like nitrogen, oxygen, and fluorine, the intermolecular attractions that we see between these molecules and adjacent molecules is typically quite a bit stronger. And so this leads to unique characteristics and properties that we might observe, like boiling point or melting point, and other unique characteristics of liquids, water in particular. When we look at compounds and we compare them on the basis of properties, their melting points, their boiling points, typically what we see is that compounds that have similar molecular weights will have similar properties, similar melting points, similar boiling points. However, when hydrogen is involved, the fact that hydrogen has only one electron means that the values that we see are typically discrepant from other comparable compounds, especially when hydrogen is bound to one of the very highly electronegative elements that we have, nitrogen, oxygen, and fluorine. Not only does it create a polar molecule, but it's an extremely polar molecule, and having an even stronger electrostatic potential, even stronger partial positive, partial negative charge means that it's going to have a greater force of attraction to adjacent molecules. Because that proton in hydrogen's nucleus essentially becomes fully exposed when it's bonded to one of those three electronegative elements, nitrogen, oxygen, or fluorine, and hydrogen itself is a very small atom, that charge is going to be very much concentrated. And so you get a very strong attractive force. It's a type of dipole-dipole force, but we call it a hydrogen bond. Now, for as strong as this is being made out to sound, hydrogen bonds still aren't as strong as actual chemical bonds, ionic bonds, covalent bonds, things of that nature. But it can hold adjacent molecules firmly together, so it can affect the amount of energy that's needed to change a substance from a solid to a liquid, melting, or from a liquid to a gas, vaporizing, boiling, and it helps to explain why we see these discrepancies in hydrogen compounds compared to those of other polar molecules of similar molecular weights. Water is a classic example. When we take a look at water, we know that oxygen is quite a bit more electronegative than hydrogen. And so what happens is you get a partial negative charge on the oxygen, partial positive on the hydrogen end. And so adjacent water molecules are going to align themselves, hydrogen on one to oxygen on another, and that attraction is going to be one of these hydrogen bonds. Well, when water freezes, when we remove energy from water in the liquid state, as they slow down and these attractive forces begin to take hold, the open shape of that, the bent molecular geometry that we see with a 104.5 bond angle is actually going to force the water molecules further apart, creating an open crystalline structure. And what this means practically is that water in its solid state at 0 degrees Celsius is actually less dense than water in its liquid state. And things that are less dense will float. So this is why our rivers and streams and ponds and lakes will freeze from the top down. If it weren't for this fact, aquatic life wouldn't survive a hard winter. So it's actually a very important property that we see, a very important characteristic, but a very unique one as well. Not many substances are like that. When we raise the temperature from 0 degrees Celsius, the ice begins to melt, and what's happening there is some of those, but not all of the hydrogen bonds begin to break. So the water molecules start to be able to rotate and shift and get a little bit closer, filling in some of that openness in the crystalline structure. And so it starts to become more and more dense. Well, at just shy of 4 degrees Celsius, just about all of those hydrogen bonds are broken in the crystalline structure, and your molecules of water are as closely packed as they're going to get. Water's at its densest. So if you have, say, a glass of ice water and you put a thermometer in it, if you hold the thermometer at the very top of the ice water, it'll be colder than if you were to plunge it all the way down to the bottom. If you went ice fishing and you put a thermometer or a temperature probe down into the ice, the further down it went, the warmer the water would get. Now, it's going to max out at about 4 degrees Celsius, but still, thinking about the lower you go in the water, one might expect it to get colder, when in fact the opposite is true. Once you hit that 3.98 degrees Celsius, the 4 degrees Celsius, as you begin to heat those water molecules more, then it behaves more like we would expect. The molecules move faster and begin to expand. But water is actually its densest at about 4 degrees Celsius. Surface tension, this is another thing that hydrogen bonding plays an important role in, although any liquid is going to have a certain amount of surface tension. What it stems from is when you have molecules that are at the surface, they only can exert a force of attraction on other molecules that are surrounding them and below them, instead of in all directions, including above them. And so what happens is the net force tends to pull the molecules inward towards the center of the liquid, and it creates essentially what acts like an elastic surface. Now we see this in the world around us. Whenever you fill a glass up to the very top, you can actually fill it so full that the water actually sits above the rim of the glass but yet does not spill out. If you're careful, you can float things that are more dense than water, such as like a steel razor blade or a paper clip. Actually get it to float on the surface of the water. It's the surface tension that's supporting that. Certain insects can walk across the water. That's because they're spreading their weight out such that it doesn't break that elastic surface, that surface tension. And it's also what explains why liquid droplets tend to be spherical in shape. They're pulling inward on one another and in all directions, and thus it's creating a curved surface of the sphere. So if we compare all the weak forces that we have, remember that all of these are drastically weaker than intramolecular forces, which would be things like ionic bonding, covalent bonding. All right, and they're only effective over extremely short distances. In fact, if you increase the distance between molecules simply by doubling the distance, the attractive force actually cuts to a 64th of the original amount. So it's an exponential relationship. You see here a relative assessment of the strength of these van der Waals forces. The dispersion forces being the weakest, that was between nonpolar molecules. Dipole-induced dipole is when you had one polar molecule and one nonpolar molecule, and followed by then in strength by dipole-dipole, two permanent dipoles. And hydrogen bonding tops out the strength list here. But remember, it's a subset of a dipole-dipole. It actually is a dipole-dipole interaction. It's just a special case of dipole-dipole where you have a molecule that contains hydrogen bonded to a highly electronegative atom, namely either nitrogen, oxygen, or fluorine.